Yo guys, what's up? So as a gravitation example, we want to be able to talk about. There's a problem in your worksheet that says it's not about the Earth and the Moon, but we'll pose it as that scenario here. There's a point somewhere between the Earth and the Moon where you could put, say, a spaceship or a rock or a satellite or an astronaut or a Volkswagen, and the net force on that object would be zero. Right? We can do net force anywhere. If we did this, at this location, there's a force that the Earth exerts on an object. So here's a mass. That's a mass M. That's a little m. Right? There's a force, a little tiny force that the Moon exerts. If we want the net force, we'd say it's F Moon minus F Earth, and that would give us something. Well, it'd actually give us, the object's acceleration at that location. All right? Now, if we look anywhere around here, someone said this the other day as an explanation for, well, actually, as an explanation for this very question. There's a place somewhere, I wish this thing would work that way, but, if I slide this way, well, what happens is FE gets smaller, FM gets bigger, and somewhere out here, those two forces are the exact same. Right, so there's some location way over here that if we put that, well, forget about putting the object there. At this location, we're going to ask what's not the sum of the forces, not the net force, but the net G. Right? And if you remember what G is, oops, gravitational field. It's gravitational field strength. All right? So notice that object, sorry, this dot is not an object. It's a location. Not an object. If we want to know what the net gravitational field is there, well, gravitational field is a vector, right? It has a certain strength, points in a certain direction. Here in this room, even where you're sitting, the gravitational field strength, or the gravitational field has a strength of 9.8 newtons per kilogram, and it points downward. All right, so we could actually write this as, well, there's G Earth, there's G Moon. I'll just write it as M, stupid. There's G Moon, and we're looking for a location, that's an M, we're looking for a location where those are equal and opposite. Okay? Well, the way we're going to write it is we have to go back to what's our expression for G. Well, G, by definition, is G M over R squared. Right? The force is G M M over R squared. But we got to here by saying the force is mg. Right? So if mg is G M M over R squared and we get rid of one of these m's, well, there's our expression for G. All right, so what we can say here is if we want our net G to equal 0, we're going to say that G Moon minus G Earth is 0, or G Moon equals G Earth. Okay? Well, that says, let me do this. Let's see if I can bounce this stuff over here. Yeah, I'll sort of go across the screen here. So if we go over to here, well, G is big G. Now, G Moon depends on the mass of the moon and how far from the moon you are. Not the radius of the moon. How far from the moon you are. And G of the Earth depends on the mass of the Earth and how far from the Earth you are. Well, let's do this. Get rid of those. All right. Now, what we do know is I'm going to call this, let's just call this, well, let's call this x. I know first block you saw this the other day, and I did it a little bit differently, just with different notations. But here's what we call our Earth, and here's what we call our moon. All right, so we could write this as, well, yeah. The thing is, we know what x is, right? So instead of writing this as two different unknowns, what we're going to do is knock it down to one unknown. Let's figure out how far from the Earth this point is. So we can write this side over here still as mass of the Earth over our Earth. We want to know how far from the Earth. And this one we're going to write as mass of the moon over, well, x minus our Earth. That allows us to go from two unknowns down to one. Our only unknown is how far from the Earth, RE. Now here's a trick. It looks like, oh boy, squared, and I gotta like FOIL that. Just take the square root of everything. Or both sides at least. Alright, we get over here, we get the square root of the mass of the moon over x minus r. Whoops, x minus r equals the square root of mass of the Earth over RE. Now, this is all, the last few steps really all just algebra. Right, so I'm going to do RE, cross multiplying, mass of the moon equals x minus RE, all that, mass of the Earth, RE, mass of the moon equals x, mass of the Earth minus RE, mass of the Earth. Get all the RE's on one side. Factor out this RE. And then RE is x, mass of the Earth divided by that sum. Okay? And I think that x is like 3.84 times 10 to the 8th meters, and I believe that RE here comes out to something like 3.56 or so times 10 to the 8th meters. So notice, we're almost all the way over there. We're 35 out of 38, whatever that fraction is, 35 over 38 divided by 38. We're 92% of the way there to the moon. So you got to be real close to the moon, okay, in order for this gravitational field strength to equal 0. All right. So I just wanted to make sure we get this, kind of get it in the video, get it on paper, as this is a problem that you are expected to be able to do. I repeat, this is a problem that you are expected to be able to do. Right? It's not always going to be with Earth masses and moon masses. It could be with any two masses separated by any distance. Right? In question 33b, you have two different masses separated by a known distance. So, yes, this will be how you end up doing it, but you got to be able to get there. You can't just do not memorize that equation. That'll get you minimal points. There's no physics so much in that. The physics is up to here, right? And then the algebra is getting to that. Okay, but just want to make sure we can, we've all seen it. All right, adios, folks. There.